Hey, math people, planes in space. We just finished lines in space, still looking at some of the basics, but this time around, at least we're graphing surfaces, right? So the way we're gonna map this out is we're gonna build the intuition, of course, go over the three main equations, and then just a slew of examples. So remember, this video is for you, Ashton. I don't know if I used that one. I think I did. This video is for you, Luca. And the point of that is to remind you that you can use pause. You can use the timestamps. Let me know if you have any questions, as usual. Let's math. All right, use your brain. Use your brain, dude. Have you tried that? Use your brain, maybe your hands as well. Why is a point in a direction not enough for planes, right? So if you had a point in space, I don't know if I have anything that could be a point in space. I do. An AirPod. I don't know. Point in space. And then a direction. Okay. Direction. So just like that way. Why is this not enough? Think about it. 3, 2, 1. Whoa. Because if I just have a point in itself and a direction, I can still swivel, right? Because this direction is still met, like the direction of, like, say, my middle finger, right? That direction is still met, but all these planes are different planes. This plane is different from this plane, so on and so forth. So I can swivel. That's a problem. With planes, we don't just need a point and a direction vector. We need a point and a normal vector. So all coming together here. The normal vector, what type of product might we need? Think about it. Because if we have a normal vector, right? So let's look at the same plane. We have a point, we can just denote that with the eraser tip. And a normal vector, I cannot swivel anymore because that normal vector, at the moment I try to swivel, that's a different vector. It's pointing in different directions. So I'm forced to be the static plane so long as I have a normal vector, not a direction vector. A direction vector is not enough. Normal vector is. All right, and then I do some drawing stuff down here. So this is just my way of coming up with, so let's use the space. Isn't it a plane? Funny math stuff as a playground for coming up with the equations, okay. So consider that if I wanted to observe that here's my point. So it's x naught, y naught, z naught. And then I have, like, my direction vector in blue. So x comma y comma z would be just another point on the plane. All right. And then I had a comma b comma c. What I want to do is I want to, so two orthogonal vectors. Yeah, I want this dot product to be 0, right? Between the normal vector, a, b, c, and then this vector, so this vector p naught to p, I can just find this vector by taking the difference, right? So that's x minus x naught, y minus y naught, z minus z naught. I want this to be a right angle. So I want to set the dot product equal to 0, right? That's the whole idea. So I'm going to do that. Here it comes, 3, 2, 1. Is that when I find the dot product to be 0, right? I am going to say that this is just strictly one of the equations of a plane. Yeah, this is just strictly one of the equations of the plane. I need the dot and cross, by the way. This vector, very clearly I need the dot right here. If I were to then multiply this out using the dot product, what I can do is I can get a times this x minus x naught plus b times this y minus y naught. Same story for c to get the scalar addition, scalar equation of the plane. All right, so clearly in the space below here, I'm trying to establish this idea. So consider this. Consider the direction vector that's on the plane. So I chose some arbitrary point, x naught, y naught, z naught, called it p naught. And then I created some arbitrary point on the direction vector and just x, y, z. And if I wanted to come up with this direction vector, it's just the difference between the two for each component respectively, right? The normal vector on this plane, I'm just calling A, B, C. And I know that any vector that I draw on this plane must be orthogonal to that normal vector. The normal vector being orthogonal or perpendicular to the plane. I need that idea. It is required, right? And I need that to be a right angle. So what I'm going to do is I'm going to take the dot product between the normal vector and then, say my middle finger here, the direction vector on the plane. I know that that dot product must be equal to 0. So that's the premise. I'm going to take ABC, dot it with pop here, I guess. Yeah. And set it equal to 0. And what that's going to give us is the vector equation of the plane. If I so we're going to need the dot and cross product here today. Here's the dot in action, very clearly within the vector equation. If I were to then multiply the respective components, just apply the dot, right, I end up getting the scalar equation of the plane. So 2 different forms right off the bat. To get the third equation out of the way, may as well do that right now. So I took the scalar equation and I just distributed. So distribute the A, distribute the B, distribute the C. You get some sort of like arbitrary constant in some ways. Just like A, X naught, B, Y naught. You don't need to track them. You can just combine them all together and just create some sort of constant D, which can be sort of like your horizontal shift in some ways. All right, that's it. We have all 3 equations. So that is the linear equation of the plane. All right, but how can we create such a normal vector? How do we create a normal vector, right? If I'm on the plane and I got one vector maybe going like this, and I got another vector maybe going like this, how can I create a normal vector that is orthogonal to both of those vectors on the plane? There's a method for this. We used the dot already, right? Here was the dot. So now we just have to find the cross. So I just find 2 vectors on the plane. Sometimes I might have to create those vectors on my own, which is not that bad, by the way. Coming up with a direction vector, very simple. It's just literally subtraction, right? Subtraction of each component. So I come up with 2 vectors, so long as I can come up with 2 vectors on the plane. Then I can just find the cross product of the 2, and I'm good to go. I have that normal vector. So this is why you need 3 points, right? That's the bottom line. If you have just 2 floating points, point and point, right, you get the swivel. But as soon as you introduce that third point, which is going to be enough to create the normal vector, right? But as soon as you create that third point, I can't swivel anymore. So long as they're not collinear, right? They can't be all on the same line. All right, oops. All right, so how many points are necessary to create a plane? Yeah, you need 3. You need 3. But think about what these steps might be thereafter in order to come up. So once you have those 3 points, what can you do to create 2 vectors out of them to create that normal vector, right? 3, 2, 1. Yeah, it's all this stuff right here. So we need 3 points. We'll call them points A, B, C. You can create a vector AB, create a vector AC. And then once you find the cross, you have yourself the normal vector. You can plug and play into your formulas right here. So I have my 3 points, so I can create my 2 vectors. How about we create vector AB and vector AC, and then with those vectors, create the normal vector, and then we'll use point A as like the point on the plane. So give it a go if you want. 3, 2, 1. So I created vector AB, right? I just followed the steps, and I got 3, 3, 3. And then I created the vector AC, so I had to make this not 9 because then they would have been collinear. I got 6, 6, 7. All right. So after I find the cross product of these 2 vectors, what I'm doing, so is I have vector AB, which might be my like middle finger, right? And then I have vector AC, which could be like my ring finger or something like that, right? So what I'm doing is then I'm just finding the orthogonal vector, the cross product, which is going to be 90 degrees to both. And that is this vector right here. So now I have my normal vector. And I can just straight up plug and play into the formulas above. This was my normal vector, right? It could be served as coefficients or as the vector without a variable. And then I plugged in my point. I chose 1, 2, 3, A for my x naught, y naught, z naught, respectively, right? So here are my 3 equations. Okay, and I just want to take a look at the graph. So I plotted 1, 2, 3. There it is. And if I were to graph 3x minus 3y plus 3 is equal to 0. Extend it into space. Yeah, there's actually I guess it's just a totally vertical line. Plotting 4, 5, 6. also on that plane, and then 7, 8, 10. Yeah, there they all are. Yeah, the z component went away because how did the z component go away? Oh, because of this match right here, which would be the coefficient of k. All right, anyway. Round 2, given the normal vector. This one's quick. You can do this one. We're given the normal vector, and then we have a point on the plane. We have all the information we need. Just simply write this in linear equation form. Not a lot of math required. Just use one of the formulas we showed earlier. 3, 2, 1. No math required, really. Yeah, so we're just using the normal vector as those coefficients, and then we have the point that we're just plugging in for x naught, y naught, and z naught respectively. I use scalar form as like the starter, and then I just combine like terms, just did some algebra to get it in its linear form. I guess for fun, we could take a look at the graph. So I'll go ahead and graph 2x, because this one has a z component. So it's going to be, it's going to have a bit of a slope as z changes. Whereas the last one had no z component. So it was just a projection of a line on the plane extended outward. Extended. All right, well, anyway. So 2x minus 3y plus z plus 13 is equal to 0. Here we go. So this is the plane this time around. We have a z component, so there is some change in z. And then if I were to plot the point 4, 5, negative 6 should exist on the line. 4, 5, negative 6. Oh, that's not that. There we go. Looking good. All right, round 3. All right, for round 3, we got a point, negative 1, 5, 0, and that's x naught, y naught, z naught. And we want to be perpendicular to this plane. So in some way, we want to use the normal vector we can pluck out of this plane, separate plane. And that'll help us come up with the line that is perpendicular to the plane. All right, so we're coming up with an equation of a line that's from my last lecture, 5a. So yeah, see how this goes. 3, 2, 1. It's not that bad. It's just more plug and play once you know the forms. 3, 2, 1. So here's the thing, is that the normal vector is perpendicular to the plane, right? So when you're asked to create a line that is perpendicular to the plane, you have that. The direction vector that we use for this line is the normal vector for the plane because they're perpendicular. So use that, plugged it into those, to the denominator for the symmetric equations form, and then I had my point, x naught, y naught, z naught. Okay, so it's really just plug and play once you know what you're doing. All right, for round 4, we're finding the vector equation form of the line again, through 5, 2, negative 2, and I want it to be parallel to the intersection of these two planes. Whoa, that's a lot going on. At least I have the point on the line, right? I just need the direction vector. So I want to utilize the normal vectors of these two planes in some way to come up with the direction vector of this line. All right, give it a go. 3, 2, 1. A little tricky. What I did was I found the normal vector of the first, normal vector of the second. And let's think about that. I have two planes, they intersect. All right. And then I'm just looking at the two normal vectors, and those also intersect. I want that parallel to the line, and I'm going to get that by coming up with the normal of the two normals, right? Because if I go normal, then I'm just back to parallel. It's kind of like the idea behind it, right? If you have a perpendicular slope and then you find the perpendicular slope again. So if you have 1/2, you do perpendicular, that'd be negative 2, and then perpendicular again, you're back to 1/2. It's kind of like that idea, that logic. So went ahead, found the cross product. This right here is a normal vector to both the normal vectors, which is then therefore parallel to the intersection of the planes. Wow. Went ahead and graphed it here. This one's a fun, I have no idea what this looks like, to be honest. I don't think I've ever graphed this one. I've always just kind of yapped and just been like, yeah, that's probably what's going on. 2x, let's take a look. 2x plus z is equal to 4. And then I have a negative x plus 3y. And then, I got a good way to think about this actually. Plus z is equal to 6. Awesome. So clearly they intersect at a line, right? A plane and a plane. It makes sense that they intersect. The intersection is just this line. Now look at this with me. If I want to find this intersection, what I can do is I can domain restrict whatever, one of them, to when the other is true. And actually, look at that. That's the intersection, right, of the two. Let's see what I did there, right? I domain restricted blue to just be true only when we're on green, right? There it is. And then I just got rid of green. So, all right. So I want this direction vector, which we can pluck out by just finding the normal of the normals. Anyway, I have what I need, and then I'll go ahead and graph the line here. So I'm going to do this as a parametric set of equation. So it'll be 5 minus 3t, 2 minus 3t, and then negative 2 plus 6t. All right. Graph that forever, or at least forever enough, and look at that. They're parallel. Not too bad, not too bad, not too bad. All right, last round here. I'm given two planes. Are they parallel, orthogonal, or neither? So, two planes can either be parallel to one another, right? Neither, and they intersect. Or, I guess one of the intersections, they can be the same plane, by the way. That is possible, but that's not happening here. Or neither. So it can be orthogonal. They intersect exactly at a right angle, or they intersect at some other angle. Of course, I can graph this and look. But so really the idea is to find a way to say it's either parallel or orthogonal. So check that in some capacity. Check that in some capacity. There's a way for orthogonal to check orthogonality. And there's a way to check for paralleleness. And if it's not parallel and it's not orthogonal, then it has to be neither. So that's my hint. 3, 2, 1. All right, so in terms of figuring out if they're parallel, you just want to see if they're scalar multiples of one another. So if we look at this normal vector, it's 6, 2, 1. We look at this one, it's 3, negative 1, 2. These are not scalar multiples of one another. You cannot multiply this by some number to get that. Because if they were the same scalar multiples, they would tend in the same way. And then you would verify to see if they don't have the same starting point, which they don't. So these are not parallel. To test if they're orthogonal, I'm just looking at the two normal vectors. I'm just looking to see if the two normal vectors create a right angle. And if they do, then it's orthogonal. And that's just not the case, right? If I take the dot between these two normal vectors, it's not 0, so it's also not orthogonal. So I proved that it's not parallel, it's not orthogonal. So it must be neither. They intersect at some angle. What is that angle? Well, I can just take the normal vectors, and I can use one of the definitions for the angle, either the sine or cosine version. I prefer the cosine version. It's just easier to use. And it comes out to this. I don't exactly know what that measurement is, but you can look it up for fun if you'd like to. Sounds like a blast. Math on.